This video presents our work, Learning to Guide Online Multi-Contact Receding Horizon Planning. When deploying legged robots in real-world, robots can encounter state drifts and environment changes. This will cause the original motion plan invalid, and online replanning is needed. To this end, receding horizon planning is a promising solution. Receding horizon planning aims to constantly update the motion for execution, guided by the planning of an extended horizon. However, this can lead to high-dimensional and non-convex problem, which is intractable for online computation. In this work, we propose to guide the execution horizon with a learned oracle that can predict local objectives as intermediate goal states. This allows us to shorten the planning horizon and achieve online RHP. To give more detail, let us consider the RHP problem from Bellman's perspective. The execution horizon can be seen as an approximation of the optimal policy, UT. Bellman equation suggests that the optimal policy should not only minimize a running cost, L, but also lead to a state, xt, star, which optimizes a value function, V. The value function directs the execution horizon by telling the desirability of a given state. For complex systems, analytical formulation of the value function is often unavailable, and we need to approximate the value function. Traditional RHP approximates the value function by computing trajectories in the prediction horizon, while the computation time highly depends on the chosen dynamics model. For instance, we can cover the planning horizon with accurate models, such as the whole-body model and centroidal model. However, these models are usually nonlinear and high-dimensional, which hinders online computation. To speed up the computation, convex inner and outer approximations of the centroidal model are proposed. However, inner approximation can fail to find a solution due to the reduced search space, while the outer approximation can violate system dynamics. Previously, we proposed multi-fidelity RHP, which employs an accurate model in the execution horizon, and a relaxed model in the prediction horizon. This ensures the execution horizon is dynamically consistent, while reducing overall problem complexity. However, this approach can struggle to compute online when long look ahead is needed. Alternatively, we can shorten the planning horizon by learning a value function model. However, learning value function for multi-contact planning is challenging. This is because the value function is defined in a coupled state environment space, which requires a flexible parameterization that can capture the landscape changes of the value function with respect to environment variations. In this work, we propose to approximate the value function with a learned oracle that can predict intermediate goal states for completing a given task based on the current robot state, the final goal and the environment. We refer to these intermediate goal states as local objectives. We then construct local value functions based on these local objectives and use them to guide a short horizon RHP. We call this approach as locally guided receding horizon planning. Next, we present the details of our approach. First, we make following assumptions. We plan centroidal trajectories for humanoid walking. The execution horizon covers a single-step motion, and thus the oracle predicts the local objective for making a step. Each step consists of 3 phases, pre-swing, swing, and post-landing. We fix the sequence of contact surfaces, in which the swing foot will land on, while we optimize the contact locations and timings. Next, we describe the oracle formulation. The output includes the target center of mass state, target contact location for making a step, and phase switching timings for making that step. The input includes the swing foot indicator, the initial center of mass state, the initial swing foot position. A preview of the environment consists of the surfaces where the 2 feet initially stand upon, and the surfaces that future end steps will land on. We parameterize each surface by its 4 vertices. Lastly, the input requires a final goal. We define all spatial quantities in the contact foot frame, W sigma, established at the position of the non-swing foot, with the orientation aligned with the surface in contact. We parameterize the target contact location with an on-surface representation, in which the target contact location is defined as the summation of 2 vectors, scaling along each of the surface borders, and we predict the scaling factor, alphas. To guide the short horizon RHP, we use terminal costs to encourage the terminal center of mass state, and the contact location, to approach the predicted targets, and we use constraints to narrow down the search space of phase switching timings, centered at their predicted values. We train the oracle with supervised learning. We use neural network to model the oracle, and we generate training data using long horizon RHP. Due to the prediction error, the oracle can lead to ill-posed state, from which the short horizon RHP can fail to converge. We mitigate this issue by an incremental training scheme, in which we augment the dataset by adding corrective actions from the states causing convergence failures. Next, we present our experiment result. We firstly use locally guided RHP, and the baseline, long horizon RHP, to plan centroidal trajectories in a receding horizon fashion, on the terrains made of moderate slope and large slope. We mark a cycle computes online, if it converges within the time budget, the duration of the motion to be executed for the current cycle. We then validate the planned trajectories by tracking them with a whole-body inverse dynamics controller in simulation. For moderate slope, the baseline can plan trajectories with one-step prediction horizon. However, half of the cycles failed to converge online. In contrast, our locally guided RHP achieved online computation for 98% of the cycles, while consuming averagely 19% of the time budget. This shows the potential of real robot control, as the remaining time budget can be used for overheads such as data transmission. Owing to the computation efficiency, locally guided RHP can maintain online computation for averagely 23 cycles over a set of testing terrains, while the baseline can barely achieve online computation consecutively. To plan trajectories on the large slope where static stability cannot be maintained, the baseline can require two-step prediction horizon. Due to this increased computation burden, the baseline only has 8% of the cycles converged online. In contrast, locally guided RHP achieves online computation for 95% of the cycles, while consuming only 18% of the time budget. Moreover, our locally guided RHP can complete 76% of the trials with all the cycles converged online, while none of the trial of the baseline can maintain online computation. To conclude, we propose locally guided RHP, which can achieve online receding horizon planning of multi-contact motions. The key idea is to learn an oracle to guide the planning of a short horizon RHP. In the future, we plan to test our approach on real robot. Thank you for watching.